Hey guys, so what I want to talk to you about today is another analogy for the charge flow through a circuit. So I want to make sure that we redefine or define maybe a little bit better than last time flow rate and flow rate and drift speed. So flow rate is the amount of charge that flows through a point in 1 second. Whereas drift speed is something altogether different. Drift speed is how fast the charge is moving. And in these analogies, we're going to look at charge as people. So I'm going to use a situation that's probably fairly familiar to you, as the moving kids from the Seton parking lot into the gym. That should be something that is more or less familiar to you already. I want you to imagine that here we have the parking lot, and over here we have the gym, and we're trying to move the entire student population from the parking lot into the gym. Now, normally there's a door there, but let's imagine for a moment that there is no door and actually we've just torn down the entire wall. All of these people in here are able to basically move at the same time, all of them through that big door. And so what we have is a very high flow rate because the amount of people that can move from the parking lot into the gym in 1 second is very high because there's a lot of room for them to move. Now, they don't have to move very fast. Like, they don't have to be like, whoosh, they don't have to be moving super duper fast in order to get into the gym in a timely fashion. Because there's such a large opening, there can be a very high flow rate, even though their drift speed doesn't have to be very high. Now, what we usually do at Seton is very intelligent. We open just one of the doors that goes into the gym. Now, because the door has a very limited amount of space, we can't fit as many people into the gym all at the same time. We're basically going from here where we can fit, that's like 20 people all at once into the gym. Instead, we just open one door so that maybe we can fit 1 or 2 people through that door and get them into the gym all at once. What happens then is the people, once they get right here, a couple of the people can still keep moving at the same speed, right? They can keep going through that door, and so they can keep walking at a normal walking speed. But then the people behind them, right? See how they get all clumped together on the outside of the gym? All those people behind them, since they can't all fit through the door at the same time, they have to slow down. So adding that one door into our circuit, big air quotes, okay, adding that single door into our circuit makes it harder for the people to get in. It adds some resistance right there, and less people can get through that point, and so it limits our flow rate. The people here can keep moving the same speed, but the people here have to slow down. So when I say that the people in here are moving faster, it's not necessarily that they have to speed up, but it might be that these people have to slow down. Okay, and then the people here, they can keep moving at that same speed, I suppose, because, they're over here. But really, they just have this less pressure. If we want the same number of people to be moving past this line as are moving past this line, then they would have to slow down. And that's where this analogy gets a little bit different from the river analogy. If we look at this as a river and we have a wide part of the river and then some rapids and then a narrower part of the river, then the river here and the river here are probably moving at the same speed, if that makes sense. Okay, so there's people trying to move through here. Because of that door, the people over here have to slow down in order to get the same number of people going into the door as come out of the door. Now, the activity that we looked at on Tuesday, I think, activity 3.4, that activity was one where we added multiple resistors. So we had like a resistor here and a resistor here, kind of like this. And this is actually close to the situation that we do have when we are moving people into our gym from the parking lot, is we have the parking lot there, and then people have to go through a door, and then they get into the lobby of the gym, but then they have another door that they have to go through before they can get into the gym. Okay, so I want you to look at this here. We see that when they encounter that first door, the people here have to slow down so that the same number of people going into the door can come out of the door. And these people, they can keep walking. Again, they're going to be moving a little bit faster than the people here. And then, once they get into the lobby, they're going to have to slow down again, because they're going to be encountering another door. So if these people, we've got 2 people coming out of this door, well, then only 2 people can come into this door again. And so what essentially happens is it makes it so that the people, when they encounter another door, it limits the flow rate again. Okay, so the flow rate decreases more with the second door. When we make it so that the people have to go through 2 separate doors, that's going to make it harder for those people to get from the parking lot into the gym. And so it's going to make them all go slower, even slower here. We're going to have more people backed up here. We're going to have them going slower here, and the total flow rate is going to drop again. So we're going to be able to get less people into the gym in 1 second, like even fewer than before. This essentially has the same effect as if we just made a long hallway. So adding that extra door would be essentially the same as making a longer door or a long hallway, where these people, they have to spend a longer amount of time kind of in a single file line. And so that means that the people here have to wait even longer to get through this door than they did before. Okay, so these people back here, they have to wait even longer, and so that makes the flow rate lower. Remember with the notes that I shared with you regarding the long bulb versus the round bulb? The round bulb was, the filament is a little wider, and it's not as long as the long bulb, which had a very long and very thin filament. The longer that filament is, the more resistance it has, and the less charge is going to be allowed to flow. So less people can flow through a longer hallway than could flow through a simple door like before. Now what we looked at on Wednesday, we looked at Unit 3, Activity 5, and that was adding doors, or rather resistors, in branches like this. Okay, now I don't have the circuit there, but you should remember that from a couple days ago. We added those resistors, what we called in parallel, or in branches. And what we saw with that was kind of interesting. We saw that adding that extra bulb in a different branch actually made our total flow rate higher, because it made our resistance lower, which is a little counterintuitive since it sounds like adding more bulbs would make the resistance higher. But when we add them side by side like this, it doesn't. And hopefully the parking lot into the gym analogy helps to make that make a little bit more sense. Basically, when we have the people encounter the door, they actually have 2 options, and this is something that we can do at Seton, but we tend to not. We could open a second door, And that allows essentially twice as many people to fit through at once as if there was just one door. And so the people on this side, on the parking lot side of the door, don't have to slow down quite as much, because there's basically two options for them to get through this door and into the gym. And so instead of just having, one or two people able to get through, we have 3 or 4 people able to get through both of those doors at once. So adding those doors side by side, or adding those resistors in parallel, it opens up an extra path that allows that charge or those people to flow through. And with that extra path there, we're actually able to get a higher flow rate. That has more or less the same effect as if we just made a wider door. Okay, we can fit twice as many people through a wide door as we could through a single narrow door. I still have a couple of minutes left, and I didn't draw this picture yet, so I'm going to go ahead and draw it real quick. I want you to imagine again that we have the parking lot over here, and let's say we've got a door right here. Okay, but we also have this big little path right there that we can get through. Okay, so we've got this little door, and then we've got all of our people coming through over here. And most of the people, they're going to be going through this big section right here. Not very many people are going to go through that little door. Now, we can imagine that this door is our resistor or our light bulb. Okay, we can make that door or resistor our light bulb. And this big wide section here, that is effectively our wire. And this is the activity that you did yesterday, or that I did yesterday and you watched yesterday, where we added that wire in parallel with one of the resistors. And what we saw was that that makes that resistor, that light bulb, go out. It essentially takes it out of the circuit. And we called that wire that we added a shorting wire, because it makes a short circuit around that resistor. Basically, if charge has two options of where it can go, it's going to go the easier way, not the harder way. And people will usually do the same thing. You might have a couple of trolls that decide to go through the single door for one reason or another, probably just to be goofy. But most of the people are going to go through the wider opening. And this is a concept that we usually call taking the path of least resistance. Okay, that might actually even be a phrase that you have heard before. Almost all of the time, animals, people, charge, air, water, pretty much anything, whether it has a brain or not, is going to take the path of least resistance, and stuff is always going to go the easiest way to where it's trying to go. Okay, so this wire basically has very, very low resistance, which is why most of the charge is going to go through that wire if we give the charge that option. And so that's why in the activity on Thursday, we didn't see that light bulb light in the circuit when we added the wire around it. Okay, I think that should be just about that. I've got a couple of seconds here to tell you to please make a discussion post. It's worth your point for today, So make that discussion post, whether you answer or ask a question is fine by me. Bye guys, have a good weekend.